Hello everyone. Today I'm very happy to share our latest work on static bug findings. And our paper title is Place Your Log Well Understanding and Detecting Log Misuse Bugs. And I'm the first author of this work. And first of all, I would like to briefly introduce myself. I'm Ryan, a fourth-year PhD candidate at the Hong Kong University of Science and Technologies. And my PhD advisor is Professor Charles Zhang. My general research interest is to use program analysis to ensure the software reliability and securities. And so far, I have first author's paper, and the topic of these 4 papers are related to the point analysis and the bug detections. And the massive code base and high concurrencies had made modern software increasingly complex. As shown in this graph, many popular software programs used in our daily life have more than a million lines of code and leverage concurrent programming to improve their efficiencies. And as a result, modern software programs are very prone to errors. According to the recent report, poor software quality costs the US economy $2.41 trillion every year. And many well-known vulnerabilities such as WannaCry, Heartbleed, Dirty Code, can affect millions of users across hundreds of countries. And concurrency bug remains the worst bug to capture because exposures of them rely on the subtle thread interleaving. And there's abundant evidence showing that software attacks through concurrency bugs are both practical and harmful, potentially leading to serious security issues. For example, Dirty Code is a software vulnerability that allows attackers to gain the unauthorized privilege of the Linux-based system, potentially leading to the data theft and the system compromise. And synchronization primitives are commonly in place to synchronize concurrent code so as to prevent various kinds of concurrency bugs and vulnerabilities. Existing work focuses on the detecting concurrency bugs, especially for the bugs induced by the insufficient synchronization, such as data race, memory corruption bugs, and typestate bugs. And unfortunately, less attention has been paid to the use of the synchronization API themselves. Specifically, we focus on the log API, which, as we know, is often undisciplined and can cause serious reliability and security issues. And in this work, we set up 3 research goals and make 3 corresponding contributions. The first one is that we propose a categories of common log misuse with the finding to their bug characteristic and the security impacts through a CVE ID-based empirical study. And then we design techniques and a static analysis framework to detect the log misuse in a precise and scalable way. And third, we perform an extensive evaluation to show the effectiveness of our tool and show the advancements over the state-of-the-art bug finding tools. And as mentioned, logs are common synchronization primitives to prevent harmful race conditions in multi-threaded software programs. And logs have explicit disciplines for initialization, use, and destructions. Systems that violate these locking disciplines can cause unexpected program behavior and even exploitable program states. To demystify the common log misuse and understanding their security impacts, we were motivated to perform an empirical characteristic study on the CVE ID of the past decades. And we search in the CVE database with the keyword mutex and logs and examine the corresponding vulnerability and their descriptions. And then by focusing on the log misuse of the log API, and then we were led with 32 CVE IDs to study and making 2 important findings. Our first finding is that there are 5 general locking disciplines violations, which can happen both under sequential and concurrent circumstances. And we define the bug pattern by reviewing their characteristic. And these 5 general log misuse include missing log release, double locking, using uninitialized logs and releasing unacquired logs, and cyclic log acquisitions. And the latter 3 log misuse can be related to the concurrencies. And in this slide, I'm going to use the bug found by our tool to illustrate the 5 general log misuse. The first example shows missing log release found in OpenSSL by our tools. Specifically, the logs acquired at the 375 is not released before executing the line 563. And the second example shows a double locking found in sense 64. And the log acquired at the line 85 is acquired again at the line 91. As shown in these two examples, one the log is acquired no matter is not released or is acquired again. Another thread which would like to acquire the same log should wait without interacting. So both errors actually happen sequentially. And the third example shows using uninitialized logs, which is found in Cherokee by our tools. And specifically, using uninitialized logs can happen when the log is entirely not initialized or initialized non-deterministically. And in this example, the log is initialized after creating the child thread. And when a concurrency error can happen when the child thread use the log before the log is initialized by the parent thread. And the fourth example shows releasing unacquired logs, which was found in OpenSSL. And when the pass condition at line 466 is satisfied and the log is not acquired at the line 473. And finally, the unacquired log is released at the line 516. And a concurrency error can happen when there's another thread which is using the same log and then is acquired by this thread. And the fifth example shows cyclic log acquisition found in MariaDB by our tool. And the function's actual worker thread found is executed by at least 2 threads. And concurrency errors can happen when when one thread acquires the log ctxt at the line 385 and then wait as statement 431 for the log entry to be released by another thread. And another thread acquired the log entry at the line 431 and then wait at statement 443 for the log ctxt to be released. And both threads cannot progress. And our second finding is that the log misuse can wreak severe havoc. Specifically, concurrent cyclic log acquisition and double locking can bring the system to hand, thereby triggering denial of service. Missing log release as a special kind of memory can cause the memory exhaustions. And releasing unacquired logs and using uninitialized logs can cause memory corruption and system crash. And we even find that in few cases, log misuse can cause a privilege escalations and other identified issues which are claimed by developers. And we also find that log misuse are often related to other security bugs such as automaticity violation, UART-free, and double-free. And this example shows releasing unacquired logs that can lead to automaticity violations specifically. And the unlock statement at line 145 should be a log statement. And as a result, the log is erroneously released 2 times. And more even worse, the function com setup that is expected to execute sequentially is executed concurrently without the log protections. And to detect the 5 log misuse, we propose Lockpick, a static analysis framework. In our formulations, we categorize the log misuse with finite state machines. And we model the state of log objects such as the uninitialized, initialized, acquire, error axis using the typestate. And we capture the state transactions or log object with a new domain-specific finite state machines. As a result, our tool can capture the log misuse by statically analyzing the program and checking the state transactions. And in our log misuse detections, we propose several customized techniques and several analysis stages. And specifically, we propose a path-sensitive type-state-based data flow analysis to path-sensitively check the type state of the lobs in the programs. And then, guided by the type state results, we reason about the may happen in parallel relations among the statement with interesting type state. And then finally, we perform concurrency-aware on-demand lob misuse detections to flag the lob misuse based on the type state violations, and thereby reducing unnecessary concurrency reasonings. And Lockpick is built upon the LVM infrastructure and Z3 SMT solver to verify. The solver is used to validate the path feasibility of the lob misuse. And our Lockpick is a Sunday implementation. That means that the tool is designed to detect bar rather than performing rigorous verifications. And tool evaluation. The first evaluation highlight is that our tool is very effective on bug finding. Specifically, we had found 203 developer conference bugs in over 80 well-checked software programs. And 184 of them have been fixed at the time of publications. And the software programs include many popular software such as OpenSSL and the Linux kernel. Also, our tools can find various kinds of bugs. For example, as shown in this graph, our tool can find at least 10 bugs for each category of the bug being studied. Also, those conference bugs are very long latent, hiding for 7.4 years on average. And as shown in this graph, 40 bugs had existed for over 10 years. And more importantly, 16 CVE IDs have been assigned for multiple bugs with high security impacts. Also, compared to the baseline such as SVF L2B2 and that's built on inflict and client state analyzers, our tool can reach very high efficiencies and reach high precision with significantly lower false positive rate. And for the recall, our tool can discover 26 past CVE ID in the C and C++ program being studied, and this result cannot be reached by the previous tool. Thank you. This is the end of my presentation.